Welcome to week 4, part 1 on data wrangling. Let me get started by describing what that means. So basically, data wrangling is a term that applies to the entire process of preparing data for doing statistical analyses. And a lot of this involves just cleaning the data and also reshaping and transforming the clean data into more convenient structures, more convenient tables or data frames for doing the analysis. Mostly we're going to concentrate today on issues involved in cleaning data. Cleaning data is going to take an enormous amount of your time in the real world, perhaps more than actually doing the analysis. You gather your data sets, and once you have gathered your data sets, you have to examine them to discover whether they have records that are just incomplete, that you can't use, whether there are accidentally duplicated records, whether within the records there are missing fields, and what you can do about that. And also, within the data that you do have, are there inconsistencies? This is particularly common with string values, where different data entry people will put in what they think of as the same information using different spellings or different notations or whatever, and you have to regularize all of that stuff. You also have to examine your data to see whether there are any outliers, and then to consider what, if anything, should be done about those outliers. All right, so on we go. I have revised our Allegheny County dog data to include a city column. The cities are generated based on the zip code, but this is not an exact association. If you start working with mapping data, geographical kinds of data in the U.S. at least, you'll discover that zip codes versus city and county and state boundaries are a very frustrating business, because a zip code is simply a 5-digit number designating a particular post office and its area of deliveries. There is not a big effort to coordinate that with city and county and state boundaries. So typically, in a given city, there will be many zip codes, and within a given zip code, there will be many cities. I live in an area called Penn Hills, which is somewhat east of Pittsburgh, and part of the area where I live is served by the Penn Hills post office, and part is served by the Pittsburgh post office, or at least it's called part of Pittsburgh. And so in the zip code that I live in, you will find both Penn Hills and Pittsburgh as cities. All right, in any case, let's go ahead and read this file in. We're going to call it dogdf, and we're going to read CSV from, and I've abbreviated the name a bit here, so it's dog data version 2 CSV, and the index column is still column 0. That is the dog's license number. Well, I forgot my important initial boilerplate code here. So I've got to import numpy as np, import pandas as pd, import matplotlib.pyplot as plt, and I also want to do my setting to make my data frames not drop columns in the middle. I'm going to pause for a moment while I wrestle up that particular command. All right, so I have found the relevant option setting command and copied and pasted it in. All right, so now let's try this reading the dogdf data frame again. There we go. And if I ask for the shape, I see that there are 34,778 records in here. This time there are 9 columns rather than just 8. Dogdf's columns are, well, it's a little awkward to look at here, but I have the 8 that we have been using: breed, color, dog name, owner zip, gender intact, age, weight, and I've also added the city column. Okay. Now, one of the first things that you want to know after you have just successfully read in your data set and displayed its shape, the shape will tell you how many rows and columns you've got, you want to find out how much missing data is in your data frame. I can say dogdf.isNA or is null, either way, to find out whether the data frame has missing data. This will generate a Boolean index. Anytime I see a value of true, that means that that particular field is missing from the data frame. Now, if there's not much missing data, I may not be able to easily see any true values pop up on the screen because we've got almost 35,000 lines and 9 columns of data. Let me just hit the Enter key. And, okay, I see that we do have some trues here down near the end. And mostly falses right up at the beginning. It turns out, as we've discussed in the past, that Boolean values can be used as integer values. A true has an integer value of 1. A false has an integer value of 0. And so it turns out we can invoke our np.sum function on this Boolean index. And I want to do my summing over the rows of the data frame because that will give me a sum of all of the true values in each of the columns of my data frame. And there we go. So in my data frame, there are no missing values for the breed, or for the dog name, or for the zip code. There are 77 dogs that have missing colors, 1,192 that have missing cities, and between 12 and 15 that have missing gender, or intact status, or age, or weight. Okay? So now I need to decide systematically what I want to do about these records that have missing data. One way of handling missing data, you know, how I want to deal with these records that have missing data, one way of dealing with them is to find the correct values. And so now we have a question of, can we find the correct values, and how much time and money is it going to cost us to go out and get correct values? Sometimes that's straightforward. Sometimes, depending on what you are studying, it's completely and absolutely necessary if it has something to do with medical risks or large amounts of money or possible military conflict or something. You want to be patient and get the real data that you need, even if it does take some time and trouble. On the other hand, for many kinds of data sets and for many kinds of analyses, you might decide that it's just not plausible to go out and actually get the correct values. Okay, so if you've decided that you can't fill in the correct values, then the next question is, do you want to simply delete every row that has a missing value? How severe is that? Well, that's going to depend on the particular data set that you have. A lot of data sets have a lot of missing values, and you find that if you get rid of all of the data, all of the rows that have any missing value, that you eliminate most of your data, which is not a very good thing for being able to do analysis. Let me get for myself a data frame of all the rows that do not have any missing values by using this drop NA function on my data frame. Drop NA has a very simple purpose. It simply drops from the data frame any row that has any missing data anywhere. dogdf.dropNA returns a modified copy of dogdf with all of those rows dropped that somewhere have some missing data. And so, as a reminder, here's the size of my original data, 34,778 rows, and the no-miss data frame, on the other hand, has quite a few fewer rows, 33,506 rows rather than 34,778. So we're missing about, looks like about 1,250 rows, roughly speaking. Is that bad? Actually, that's kind of surprisingly good to have that relatively little missing data in a real data set. We can do a calculation to figure out what percentage of our data we lost. And to be proper about this, I ought to access the sub-zero items of these shape tuples. But I basically ran out of space on my slide to fuss around with all that, so we can just do it manually. We started out with 34778 records. We ended up with 33506 records or rows, and that means that the fraction of our original rows that we lost is that subtraction divided by the original size, and I'm going to multiply this by 100 to convert it into a percentage. So we have lost a little bit less than 4% of our overall data by just doing this blanket elimination of every row that has any missing data. All right. Can we do something that's a little less drastic than that? What if we look for rows that have several missing values and just decide that we're going to eliminate those rows and then see what we can do to patch up the rows that we have remaining? So we can from our dogdf.isna Boolean index, as we did before, we can compute the total number of trues, which is the total number of missing values in the columns of this. But let's sort these values in descending order, so that the topmost values will, so that the topmost numbers here will be the number of missing values for various specific dogs, for various specific rows. Okay. Now I can use, when I do the sort values, if I don't want things in ascending order, I can use this option, ascending, and set it to false. So I'm saying ascending equals false because I want these things to be in descending order. And I'm going to display just the upper 15. All right, so why did I randomly pick 15? Well, I didn't quite randomly pick 15. I noticed that these attributes here, gender, intact, age, and weight, have at most 15 missing values. There are at most 15 records with missing values. There are a lot more for color and a lot more for city, but let me just see if I can identify and do something about these dogs that have other attributes missing. All right, so there we go. Went off the top of my screen slightly. Come back, come back. All right, so here we have several dogs in which the columns have 5 missing values. All right, now that's pretty severe. Remember that there's only 9 columns in each row, and so here we're missing more than half of the data. Let me take a look at those particular records. I observe that these things appear to be in some kind of sequential order. If I start from 371-4304 and continue up to past 371-4320, that should give me those particular rows. All right, so let me use my slicing with rows. So dog df.loc for rows, and I'm going from, I want this as my initial row, 371-4304, and I'm going up to, but not including, let me just pick a value that's just beyond this value here. 371-4321, I'll say. 371-4321. Let's have a look at that slice. Oh, very interesting. And what we see is, all right, this upper part of the output looks kind of choppy because the display wants to display 1, 2, 3, 4, 5 columns in the upper half of the output, and then the remaining 4 columns in the lower half of the output. But what we can see is that for all of these values here, the gender is missing. Okay, so gender is not a number. Gender is missing for all of these dogs. And the intact status, age, weight, and city are also all missing for all of these dogs. So that's an indication that somebody really made a mistake putting this data together. And I think we can safely just eliminate all of these records from consideration when we're doing our analysis. So what we'll do here is get a subset of dog DF that goes up to the record prior to the start of the sequence. I can also tell, by the way, if I just display the whole dog DF, that the end of this sequence is the end of all the data. That's why I can get away with asking for a slice of everything up to, but not including the beginning of that, those last several records that have so much missing data in them. Let's give this a try. So I'm going to say, let's revise dog DF to be dog DF dot loc of a slice of all the records up to 14033. Okay, and now if I look at the size of this, the shape, I should say, you'll see that, yes, I have lost I have lost 144 rows. That seems like too many. I should have only lost 12. All right, so let me pause for a moment. All right, well, I see the problem. I simply made a typo in the end of my slice. This should go, this should be 303 at the end, not 033. So that's why I was losing an extra 170 rows. Let's try this again. So now dog df.shape is 34634. Uh-oh. Okay, so previously I made a simple typing mistake, and now I have made a much stupider mistake because, and I have mentioned this in class at least a time or two, you need to be very careful if you are starting with a data frame and modifying using the same variable to refer to the modified data frame. You need to be very careful not to make mistakes because there's no convenient way to back up. All right, my this dog DF only has 34,634 lines, rows in it, and consequently, when I ask for a slice that goes to the end, well, there's only 34,634 rows that it can give me. I no longer have access to these 34,778 rows. So I'm going to need to pause and start over again and catch up to this point. All right, well, starting over again was not actually that difficult, as it turned out. All I needed to do was to reread the data file over again, and all the analysis of the missing values in the data frame are still valid. So all I needed to do was to select this slice with the proper ending, and now I have the data frame of the size that I expected. 34,766 rows, which is exactly 12 less than what the original data frame had in it. All right. Now, if I reanalyze how many rows there are with missing values, dog df is na axis equal to rows. Good. I see that I have significantly reduced the number of rows remaining in my data frame that have missing data in the gender, intact, age, and weight columns. There are still a few in the age and weight. But just eliminating those 12 crummy rows gave me a much better result. All right, so now that we've reduced the burden of rows with missing values, is there something that we can do to fix some of these missing values? Well, let's have a look. We know that we have missing values in the age column and in the weight column. So I can simply display the specific rows that are that do have missing values in those two columns. So dog df sub age dot isna is my Boolean index, and I'm going to use that Boolean index to select rows out of dog df that do have missing values. And it turns out that there are 3. Okay, I've got these 3 licenses here, and let's see. So all 3 of these are missing their age. Okay, so the age is missing from all 3 of these dogs, and the weight is missing from 2 of these dogs. Now, if I just ask for the dogs that have missing weights, dog df sub dog df of the weight column dot isna, once again, I have 3 rows. A couple of these rows have missing ages, and they all, of course, have missing weights. In fact, if we compare, what I have on my slide here is an abbreviation of this output, ignoring all of the columns earlier than age, weight, and city. What we can see is that 2 of these dogs are the same. 2 of these dogs have both missing age and missing weight. All right, so let's see what tools Pandas provides me for trying to do something about these missing values. And I will give you a spoiler. These are all fairly pathetic, but you know, they are what's available. So to illustrate these so-called fill functions for putting values in place of these not a number values, I want to create a very small little data frame to illustrate these various facilities. So this guy is just plain df, and df is a data frame that contains the value 1 in the first slot, first row, and then not a numbers. Not a number is defined in NumPy, so np.nan for the next 2 rows, and 4 for the final row. Oops, forgot my square bracket there to conclude the list. And I also want to name my columns. There's only one column, but I'll name it the val or value column. So here's my trivial data frame. The most powerful or thorough or whatever of these fill functions is fill-na, which just fills some value, in this case the value 7, into all of the Nada numbers. This does not happen directly in the data frame itself. What we get back is a modified copy of what the data frame would look like if all of these Nada numbers were replaced with 7. All right, so as I said, df itself is not changed, but we see that for row sub 1 and row sub 2, fill-na would have put 7 values in there. Now, it turns out that fill-na and many other functions that allow you to manipulate values in data frame rows and columns provide an in-place keyword argument that you can use to specify that you do actually want the statement to modify your data frame directly. I don't want to do this with my original df, so let me make a copy of df called df2, and then we'll see that if I say df2.fillna with the value 7 and in place equals true, that does directly modify df2. Okay. Otherwise, most of these functions simply return a modified copy of the original data frame. Let me do another one here. So I'll say df3 gets df copy. I can modify df3 without using in place equals true by saying df3 gets the result of df3 fill-na 7. All right. So df3.fillna 7 returns a modified data frame. And what I'm doing here is I'm saying I want to use the same variable name to refer to that modified data frame. So that's the alternative to using in place equals true. Here's a little more ambitious approach. I am actually going to compute the mean of the non-null data values in the data frame. Here's df. There are 2 non-null values in here, 1 and 4. So the mean of those is 5 over 2 is 2.5. And if I say, all right, I'm going to fill the missing values with the mean value of the non-missing values in the val column, and there we go. So the Nada numbers there are going to replace 2.5. Again, though, this isn't directly modifying df. It's just showing me a modified copy of df. Another thing you can do, which is all right. I was going to say, which is ridiculously silly. Perhaps I shouldn't say that. This is called the forward fill, and what it does is when it encounters a Nada number, it uses the preceding value to fill in forward. So df.ffill. Notice that it doesn't take any argument because it just uses whatever value exists and fills that in forward. If I had a much longer data frame here with a bunch of Nada numbers below the 4, then those would get filled in with the 4. All right, so here we are. These Nada numbers were forward filled in with this value of 1. And surprise, surprise, there is a backward fill function as well. bfill, which is, in my humble estimation, equally silly. I suppose you might be able to get away with using these for time series kind of data, where if you don't have, if you need to use a value for every day, for every hour, for every minute, whatever it might be, and you have some missing values, and the values are not jumping around so much that it makes a lot of difference what you use, then I suppose this forward filling or backward filling might make some sense. I will confess I am always extremely skeptical of modifying data, modifying missing data. All right, and here we have the most sophisticated one of all. Well, the most sophisticated one that I'm showing you, which is the interpolate. Now, let me redisplay df first. So there's df. If I say df.interpolate, interpolate looks at the values that do exist and tries to provide a smooth line to fill in the missing values. All right, well, I randomly chose a very easy example here. If we start from 1 and 3 steps later we're up to 4, the implication is that each step adds 1. So the interpolation figures out that, okay, to interpolate between 1 and 4, I'll use a value of 2 for row 1 and a value of 3 for row 2, and that gives a nice smooth result. Well, in our case, for the age and the weight of dogs, these fill functions don't make any sense at all, because the previous dog's age or weight is not going to make any sense for the age or weight for a current dog. The current dog is very likely a totally different species and a totally different age, and therefore would have a totally different weight. So we're not going to be able to use these fill functions. And since there are not too many, let's simply drop these rows that have these missing values. Okay, so we can obtain the index of the dogs that have missing values for age by using a Boolean index. All right, so we've got dog df sub age dot is na, and that gives us our Boolean index. We can then apply that to dog df, and from that, okay, so that gives us the 3 dogs that have nada numbers for age, and from that, in turn, we can obtain the index of this reduced set of 3 dogs. Dot index. Okay, so there are the indexes of the 3 dogs that we need to get rid of for having age values that are not a number. We can feed that list of dogs directly to the drop function. And here's another place where we can use in-place equals true so that we don't have to, so that the change takes effect directly in the dogdf data frame. All right, so let me go ahead and do that. Okay, so dogdf.drop. And now we need to give the indexes of everything that we want to drop, which are these. And we're also going to say in place equals true. Whoop, parentheses. There we go. Let's go ahead and do the same thing for, there's one dog remaining that has its weight equal to not a number. Let's just go ahead and take care of that one as well. Just change age to weight. Okay, and now when we check dogdf.shape, we see 34,762 rows, which is 4 rows fewer than what we previously had. So we have succeeded in eliminating those 4 dogs that had missing age and or weight. And now if we check the not a numbers remaining and p.sum dogdf.isNa axis equals rows, so we get this sum over the sum over the rows for each of the columns of the remaining number of dogs that have not a number values, and we see that only color and city remain having not a number values, and that may be that may be okay. It's not clear what kind of analysis we would be able to do with colors, and we only have 1,180 cities that are not given, that are not a number. We could perhaps do some more poking around online to find those cities, or we could just eliminate those records, or we could just not bother analyzing cities at all, whichever. All right, onward ho. The next thing we want to do, now that we have dealt with trying to figure out what to do about missing values, is to see whether there are any duplicate records. And conveniently, Pandas provides a function that searches for duplicates. This duplicated function. Now there's a typo on this slide here. The duplicated function actually returns a Boolean index, which we then need to apply to the data frame itself to get this list of duplicated records. So let's see that first. Dogdf.duplicated. And of course we don't, these are all false because there are very few duplicates in here. But if we apply dogdf, if we apply that Boolean index, dogdf.duplicated, to dogdf, we see that there are 2 rows that are duplicated. Labrador retriever named Merle, color Merle, and name of Molly, and also a Labradoodle who is black named Gus. Now, I am very curious to confirm that these are duplicates, so let's use a sort of intricate Boolean index here to check on this Labrador Retriever Merle color and name Molly. So I was unaware that Merle was a color, but it is a mixture of color. The Australian Shepherd is a dog that typically has this kind of coloring scheme. It's sort of like brindle is a pattern, not really a color per se, and Merle is a pattern, not a color per se. Anyway, so let's look in the DOG-DF data frame for all records that have a dog breed of Labrador Retriever, a dog color of Merle, and a dog name of Molly. That's what's happening here. All right. I need one set of parentheses to contain this entire complex Boolean expression. So here I have these red parentheses surrounding breed Labrador Retriever and color Merle and dog name Molly. Let me go ahead and hammer this in. DOG-DF of breed is Labrador Retriever. And DOG-DF sub color is Merle. And DOG-DF sub dog name, whoop, forgot my quote, is Molly. All right. And, all right, so now what did I mess up? Labrador. Misspelled retriever. Silly me. Try again. R-E-T-R-I-E-V-E-R. There we go. There. Hey, what did I do now? All right. Oh, Molly is uppercase. I'll get there. I should have just copied and pasted from the notes. O-L-O-Y. All right, Molly. Shazam. Okay, so here we have, with the license 3661913, Labrador Retriever, color Merle, name Molly, owner zip 15102, female, false, intact status, age is 112 months, weight is 66 pounds, city is Bethel Park. And we can see that for this other dog license, we have completely identical information. So somehow we got information about this one dog into our database 2 times. And I'm going to assume that the same thing is true for our Labradoodle as well. So, having done this complex thing to identify all of the records about the Labrador Retriever named Molly, now I'm going to do much more primitive things and just drop these 2 records by typing in their license numbers. DOG-DF.drop 3661914, 3661914. And I want to do this in place. And we'll do the other dog as well. That was this Labradoodle. So I'll copy and paste that number. All right, so now if I look at dogdf.shape, I should have even two fewer records than before, 34760 instead of 34762. All right, so now we've taken care of accidental duplicate data. What data in here, even though it's present, might be inconsistent? Well, maybe the color, maybe the dog name, maybe the city. We should check these to confirm that the names of the cities are consistently spelled, the names of the dog are consistently represented, that the colors are reasonable. Let's find out about the colors of the dogs. And I'm going to use unique again, because I only want one occurrence of each of the colors. All right, so I'll get this fairly lengthy ND array. And as I scroll back through here, I notice that although a lot of dogs have individual colors, brown, white, black, sable, gray, a lot are multicolored. White, black, white, yellow, white, brown, black, brown. We also have some color patterns that aren't technically individual colors, like brindle. Brindle is a color pattern. Likewise, merle, as I mentioned, is a color pattern. And if we read through all of this, we discover that we do have some not numbers in here. We do have one color that appears to have been typed in incorrectly, because all of the other colors in here are all caps. I suspect that we only have one lilac-colored dog, so it probably doesn't matter. But we will get that made all uppercase so that it matches up with everything else. Now, I would like to be able to take these colors take these unique colors, and I would like to be able to sort them so that it's a little easier for me to read through these with my eyes to check that the colors are consistent and make sense. But unfortunately, because of the not a number that we saw, and there may be some other not a numbers in there as well, I'm unable to sort this thing currently because I've got a combination of strings and not a numbers. Well, so let's change that not a number for color to an empty string to represent an unknown color, all right? And for this, we're going to use a function called replace. Okay, so and with replace, it turns out that you can't use in place equals true. So we will take all the values in the color column, and we will do a replace of nan with an empty string wherever nan occurs. That will return a modified column, and we're going to save that modified column back into the original dog subcolor dog df subcolor column. So dog df subcolor is going to be replaced with dog df of color, in which we're going to do a replace, and of course I'm running out of space, so I'll type my parenthesis and hit the enter key. Now I can type in to replace to identify the thing that's currently there, which is np.nan, and the value that I want to replace that value with, which is the empty string. Now, it turns out that you can treat these as positional arguments. You can just say replace np.nan, comma, quote, quote, and that also works. But let me do this in a more formal way. All right, and so now if I get the colors in the updated column, the unique colors, I can sort this now because the nans, the not a numbers, are gone, and now it's going to be a little easier for me to read this result. Okay, so I'll scroll up, and sure enough, here we have our empty string that comes ahead of all the other colors. So this is this is for every dog whose color is not reported. And we've got apricot, beige, black, black with white, black blue, black brindle, black brown, on and on and on. We do have other in here, which is not very descriptive. It's some other color other than the many colors that have been shown, and we also have lilac with its lowercase letters. All right, so now we have a decision to make. Should we do anything about the blank colors, about lilac with these lowercase things, or with other? Well, frankly, we probably would not be able to obtain the actual colors of these dogs without at least making phone calls or whatever, which we're not willing to do. Lilac we can fix, just convert that to uppercase. Other, again, other is basically the same as blank. It means that we just don't know. So let us update all of the colors to their uppercase equivalent. So this is a cool feature. If you have a column that contains all strings, even though you'll notice that those strings are stored as objects in the underlying ND array, you can use the .stir attribute to access any of the string manipulation functions. So we are going to update the dog.df color column to be the existing colors, but converted to uppercase. And this will only affect lilac because all the other ones are already uppercase. And so now if I look at the unique colors in this column, I will see somewhere in here lilac. Okay. So we have succeeded in converting lilac to uppercase. All right. Now we can do a similar kind of thing with dog name. We've already seen some examples of some strange dog names. If we use dog name unique and sort the list, we had seen previously that dot space major is the initial name in the sequence, and Shunka in lowercase is the final name in that sequence. We can patch these up the same way we did with the colors. Frankly, it's repetitive, and so I'm just not going to bother with that. Let's move on to taking a look at the cities, which are a little more interesting. Now, the cities, first of all, we still have this not a number problem. We do have a number of cities that are not given. And so we're going to use the same trick that we did with the colors to replace these not a number values with empty strings, so that every single value contained in the city column is a string. All right, so let's do that first. Dog df sub city gets dog df sub city, in which we're going to replace, this time around, I'm just going to use the shortcut. I'm going to just say np.nan as the thing to be replaced, and empty string as the thing to replace with. And now, when I get all the city names from that column, the unique city names, dog df, whoops, and sort these, I'll be able to see all kinds of cities around Allegheny County alphabetically by name. City names. Here we go. It's a very long list, 53 lines. And the empty string for any of the cities that were formerly not a numbers. Allegheny, Allison Park, Arsenal, Aspinwall, Avalon. These are all either cities or neighborhoods around Allegheny County. And there's some oddball things in here. If we read this carefully, we discover, oh, look at this. Here we have East McKeesport, or East McKeesport. So it's the same city, but it's spelled two different ways. And the spelling without the space between the Mick and the Keysport is the correct spelling. So here is a place where we're going to want to replace the wrong spelling with the correct spelling. Similarly, if I continue on, I will find, let's see, here we go. Mount Washington spelled out, or Mount Washington abbreviated. And actually, I just noticed that we have Mount Oliver spelled out and Mount Oliver abbreviated. I didn't even notice that one before, so it's not in my example. And similarly for some other cities. So we can use the replace method to replace multiple incorrect spellings with the corresponding correct spellings by making use of a dictionary. So what we're going to do here is create a dictionary called Bad to Good that uses misspellings as keys and the corresponding correct spellings as the values associated with those keys. And since I spotted Mount Oliver, I'm going to add that to my dictionary. So let's build this bad to good dictionary. All right, so instead of East Mick Keysport, I should have East McKeesport. And then instead of Mount Washington, I should have the spelled out Mount Washington. And we'll do the one that I just spotted, Mount. Let me go back up and find that one. Come on now. Where is it? Where is it? Where is it? Mount Oliver. Okay, Mount Oliver. Mount Oliver with the abbreviation should be Mount Oliver spelled out. We've got some hideous misspellings of Pittsburgh in here with the H missing. So we'll make sure we put that back. And then finally, Upper St. Clair, spelled with an abbreviated Saint versus spelled out. So, on the one hand, on the one hand, it's satisfying to be able to do this, but it is also, it is a pain in the rear. It is a pain in the rear. All right, so now, notice our replace function here, and we don't have to worry about the first argument and the second argument. We've got an entire dictionary of first arguments, that is, things to replace, with the corresponding things to use as replacements. Okay, so dog df sub city is going to get dog df sub city with the bad city names changed to the good city names. And if I now double check by looking at the unique city names, I will notice, I didn't sort this, but that's okay. I notice Pittsburgh is correctly spelled now. Where else? Mount Oliver is correctly spelled. Upper St. Clair is correctly spelled. We'll assume that all of the correct changes have been made. All right, so that does some cleaning up of some inconsistent values. Next on the list, we do have numeric values. Are those numeric values, are there outliers among these numeric values? How can we find these? How can we repair them? Well, let's take a look at the age and weight columns here. So I'm going to say dog ages gets dog df sub age dot unique. Bit of a theme going on here. Dog ages dot sort. And now this is going to be a very long list. 192. Let's just look. If we're going to have outliers, the outliers are going to come either early or late in this collection of ages. So let's take a look at dog ages up to, but not including sub 10. Well, actually, that looks okay. I've got ages from 1 month, 2 months, 3 months, 4 months. And dog ages, let's look at the last 10, minus 10 colon. And those look all right as well. So it doesn't appear obvious that we have any problems among the ages of the dogs. Now, we may have problems among the ages of the dogs, but it's not clear just from looking at the range of ages that we've got a serious problem. If we had a negative age, or if we had an age of like 360 months, 30 years, then we'd consider that we probably have a problem. But these ages look okay. So let's have a look at the weights. Same deal. Dog weights is dog df sub weights. Weight dot unique. And we will sort these. And again, look at the first 10 unique weights. Well, here we have an outlier for sure. And this, of course, is my own error. When I was assigning weights to dogs, got a little carried away, and I made some weightless dogs. So that definitely shouldn't be the case. And if I look at the high end of the dog weights up from minus 10 to the end, here I've got, well, these are big weights, 201, 202, 220, 272. That seems a little extreme. All right, I have personally owned a dog that was 180 pounds, and these other weights are not completely out of control for things like Great Danes or other very large, giant breeds. 272 seems pretty high. So let's fix these dogs that have a weight of 0. Or if we decide that fixing the weights is not appropriate, we can just delete all of these rows that have a weight of 0. But let's instead do the replace thing, and we'll just arbitrarily say that the weight of any dog that is currently weightless has to be a minimum of a pound. So we will say, let's replace 0 with 1. All right, and now we have no more weightless dogs floating around our community. Now, for the big weight, well, that is a really big weight. That's true. But the weight depends, of course, on the breed and the age of the dog. other weights that we see in here, like, 184 is a, perfectly reasonable weight for a really big Great Dane or a really big Cane Corso or something like that. It would be a little bit too large for a Chihuahua. So if we got a Chihuahua in here that has a weight of 184 pounds, that is a problem. So let's, instead of just using an arbitrary cutoff for the maximum weight, it was entirely reasonable for us to assume that a minimum weight of 0 was too low. So we just took care of that briskly. But here, let's, instead of choosing some arbitrary cutoff, let's find out the mean and the standard deviation of all the adult dogs. And then we can test for dogs on a breed-by-breed basis that have reported weights that are, let's say, 2 standard deviations or more above the mean weight for that particular breed. Okay, so we are going to get this table of mean and standard deviation of weight for all of our breeds. Dog DF, sub, dog DF, and we only want adults. We had previously somewhat arbitrarily decided that 18 months was a good low end for adult dogs. Many dog breeds are adults, around 12 months, but especially some of the larger breeds keep growing for a while. We will group these by not capital. We will group these by breed and from within the breed, from within that breed grouping, we are just going to select the weight column. And now we want to execute both the mean and the standard deviation, so we're going to use our aggregate method and provide a list of the names of the functions that we want, mean and standard deviation. And there we are. "52 lines, makes sense. We've got 50 breeds. First 2 lines are just some header stuff. And then for each one of the breeds, in alphabetical order here, we've got the mean adult weight and the standard deviation adult weight. These first several dogs are pretty large, but let's go down and find our Chihuahua. Okay, so a Chihuahua has an average age of 4 pounds and a standard deviation of 3/4 of a pound. All right. So as I said, if we find any 20-pound Chihuahuas, that's almost certainly an error. Okay, now I want to this table that was just generated onto the screen. I want to store that into a variable. This thing is, by the way, a data frame. Okay, so let's repeat this. But create a variable to refer to it. Breed, weight, mean, and standard deviation. Mu for mean. I'm also going to define a function called heavy. Heavy is going to be a Boolean function that will return either true or false. And you pass in a particular breed name and a particular weight. And the heavy function will return whether a dog of that breed at that particular weight is considered heavy. And by heavy, we are going to mean that it is 2 standard deviations higher in weight than the average. There are still going to be dogs that are 2 standard deviations heavier than the average, but this is a pretty reasonable place to look for outliers. All right, so let's go ahead and get this in. I'm going to just type this in and pause for a moment. Okay, welcome back. I was pretty sure you wouldn't mind not watching me type in that long function. All right, so we pass in a breed name and a weight. We look up the average weight for that breed, and then we test. We create a heavy weight, which is the average weight plus 2 standard deviations of the weight. If the weight that was passed into the function for this particular dog is greater than that threshold of average plus 2 standard deviations, we return true that this dog should be considered heavy, otherwise false. All right, so let's go ahead and apply this thing now. We're going to create for ourselves a column that we can get rid of later. And this column is going to be created from a list comprehension. In the list comprehension, we're going to return either true or false, depending on whether the breed's weight is considered heavy. For the breed and the weight coming from dog DF, and here I'm using a fancy index on those 2 columns, the breed column and the weight column. And I want to get the values of those breeds and weights. Okay, so that runs, and we can check dog DF is heavy. Okay, mostly false. Most of the dogs are not heavy, but if we ask for dog DF sub using dog DF sub is heavy as our Boolean index, we see that yes, we do have 743 heavy dogs, or at least potentially heavy dogs. Okay, here we have a Havanese dog, a Pinscher, a Boxer, a German Shepherd. Later on we have a Shih Tzu, and let's see if we can spot that Shih Tzu. That Shih Tzu okay, well, we can find it. 3713818 is our Shih Tzu. And (3713818). So there is our Shih Tzu. And this poor thing weighs 16 pounds. For a Shih Tzu, that is pretty heavy. But it's not completely out of control, so that may not really be an outlier. Okay, well, that's all we're going to do for today, and we'll continue with this on Thursday and also move into some other topics.